Hi, hello.
Professor Hong.
Hi. Nice to see you. John, Mr. Lin has helped me set up the PPT and
how about this one?
do you want two? We can do two.
I think for this one, will you use the mouse to as a
No, I'll probably do this.
on that? It's easier for you to switch.
Yeah,
this one.
this one.
Okay, then no problem.
Yeah.
Because sometimes it's hard for you to.
Oh, I see. Yeah, craning my neck. Not giving me a hand.
Then we can switch.
But it's up to you if it's more convenient for people in the room.
Yeah, I think it's okay for
Okay.
everyone, but it's just for the speaker, to the top.
Yeah.
No problem. Hey,
没合感，这个还有，
this is the one. This 这个不要，
这个会看。
这个不要看。好，
哎，是品杰呢？黄同学们，
小心点。
我好害怕。
理解我。
人家做到会不会是品杰？啊，这样可以。
OK，
把你，然后在一旁的就可以直接把你踢。
这就是
多找人领导
OK
简历，
还有就是
好，为什么我不被踢到？
这样的。OK，第四个。
Okay. Are all of these your students or?
Yeah, oh, yeah, they are registered.
Oh, okay, all four.
Yeah,
All
also
five.
no, only the four students.
Oh, okay.
Yeah. And she will be a new graduate student for Professor Moon's.
Oh, in the fall.
Moon's Professor Moon's group.
Okay.
Yeah, working on that.
Great.
Still
还有，
还有有力，
这个厉害。
他这时间还没到。It's still early, but
Yeah, no problem. I'm still cooling down.
So you just coming from home?
No, actually I was working on campus.
Okay.
Her name, in English is Helen. Chinese, Kang Wei. No,
Last name is
Liu.
可以。
猜到的人知道吗？Okay, no problem. Okay, good afternoon, everyone. It's my pleasure to introduce you, Dr. Stefan Griffith, for a short lecture. Just briefly, it's just for lecture, not for like a paper's seminar.
You will have an exam later.
Take home exam. Okay, Dr. Griffith graduated from Indiana University in Bloomington, and his major is in your department is School of Public and Environmental Affairs. And after he got his PhD, he moved to Hong Kong University of the Science and Technology as a postdoc. But after 2 years, he became a program manager of analytical chemistry for graduate student program. But around 4 years ago, he moved to Taiwan with his family. So currently, he is working as an assistant research fellow in National Central University. Okay. So kind of know his background with them. And then let's welcome Dr. Griffith for his lecture.
Okay, thank you. Thank you. Excellent job with my history. Thank you. Would it be better if I use a microphone?
I think it should be fine.
Oh. Hi.
I
Hi, Stephen. So you will be the person in charge of this today? Okay.
We just finished the introduction.
Oh, you already did. I'm sorry, I missed that.
No,
But that's okay.
I didn't know you would be here.
I saw somebody outside. Let me just see if they want to come in. Okay, and I think I'll leave my mask on. I'm not sure what the common practice here is. Lecturers still leave mask on, it's okay?
Yeah.
Okay. I think the microphone helps, so understanding. All right, well, thank you for the introduction, Professor Hong. That was really great. If you missed it being moved, I'm really sorry. I'm Dr. Stephen Griffith, as mentioned. Thank you for inviting me here to lecture. Thank you to everyone for attending. I'm really honored to have this opportunity. So today I'm going to lecture on some of the basics of tropospheric tropospheric oxidation chemistry. Okay, when we consider oxidation chemistry in the areas where we live, in the urban areas, we really should think about all of the different sources of air pollution that impact us. Okay, and so I'm showing you some of the typical air pollution sources that impact Taiwan. Okay, industrial sources, petrol stations, power plants, vehicle emissions, all these are pretty common. And these are, of course, driving some of this oxidation chemistry that we're talking about. I'm also showing you a really beautiful picture of the Taipei Basin. It is beautiful, but you can kind of spot a little bit of a brownish haze settling over the city, particularly on the western part over Taipei City and New Taipei. Okay, so talk about that pollution. So for this topic of tropospheric oxidation chemistry, I really want to focus on two concepts today. One is the chemical lifetime of these pollutants in the troposphere, and the basics of ozone formation chemistry in the troposphere. Okay? So going back to that really dirty vehicle that we saw earlier in the first slide, we can expect that it's spewing out a multitude of pollutants, right? Just emitting a lot of things. Some of those emissions are of criteria pollutants. These are pollutants that are closely tracked by governments. Things like carbon monoxide, nitrogen dioxide, particulate matter, PM2.5. Okay, we can expect all of those emissions from this source. And then we also should expect volatile air toxics. Things like benzene, toluene, xylenes, all these really nasty compounds we can expect from vehicle emissions as well. So in these areas with really strong emission sources, we can expect the pollutants will accumulate in concentration, right? Luckily, our atmosphere has a self-cleansing mechanism to deal with some of this pollution, right? What I mean is that if we didn't have this cleansing mechanism, the pollutant concentrations would be even higher. Okay, and so this mechanism is oxidation. So as we have all these emissions from factories and vehicles and everything, the pollutants, which are sometimes very toxic, sometimes insoluble, very annoying for us to manage in the air, through oxidation, through reaction with oxidants, they will be converted sometimes to less toxic and more soluble forms. Okay? Essentially cleaning the atmosphere, and then eventually they are removed more easily deposited out of the atmosphere. Okay, so cleansing the atmosphere. Of course, this does incur some consequence. Okay, it does produce, in some cases, more acidic compounds, which then contribute to issues like acid rain. Okay, but in terms of the atmosphere, it's definitely a powerful self-cleansing mechanism. Okay, so what are some common tropospheric oxidants that we should be thinking about? Well, there's of course oxygen, O2. Okay, and then there's actually a lot of radical species as well that are really important. A radical is a molecule or an atom with an unpaired electron. So it's very reactive, and you can think of this as eager to attack other molecules. Okay, so this is important because we need our oxidants to attack the pollutants, to scrub them from the air, right? Just like we're cleaning our clothes, okay, we're thinking of scrubbing our clothes, the oxidants are scrubbing the pollution. They're the detergent of the atmosphere, okay? And so in terms of those radical species, hydroxyl radical, OH, is really important. Nitrate radical, the halogen radicals. Does anybody know what this one is here in the middle, this red molecule? Ozone, good, great, super. So ozone is made of 3 atoms, 3 oxygen atoms. It's a branched structure like this. It has a double bond between 2 of the atoms, and that double bond can be on either branch. Okay, so yeah, this is ozone, a powerful oxidant as well in the atmosphere. So which of these oxidants really should we focus on if we want to understand, talk in more detail about this oxidation chemistry in the troposphere? Well, we can revisit this molecule here, benzene, which we mentioned earlier. It's a real nasty thing. A known carcinogen, so cancer-causing agent, comes from vehicle emissions. It also is common in high concentrations around petrol stations where we have evaporative emissions from fuels. So what I want to do is show the relative reactivity of these different oxidants towards benzene. Okay, so I'm making them relative just to the reaction of OH and benzene. So that's why OH has a value of 1 here. And so if we read it in that way, we can understand that ozone is 2,000 times less reactive to benzene than OH is to benzene. The nitrate radical is about 20,000 times less reactive. Okay? Now these relative reactivities I'm listing here are for assuming some daytime oxidant concentrations that we might see. Okay? So this is not a set value here, but just a rough daytime estimate. But what I'm trying to convince you of is that when we talk about oxidation chemistry, we really can focus on the OH, the hydroxyl radical, as one of the most important species to consider. And the hydroxyl radical has an important characteristic. It's really dependent on the availability of light, okay? Light, solar radiation. And what I'm showing you here is that some data from Germany, actually, and you can see here on the y-axis are OH concentrations, and on the x-axis are a photolysis rate that's important for OH production. You can think of it as a UV light flux. So as the light flux increases, we see the OH concentrations increase as well. And as the light flux diminishes and gets closer to 0, we can also see the OH concentrations continue to decrease. So basically, at nighttime, the OH concentration and the oxidation from OH we can assume is almost irrelevant. So what is the daytime? So we know it's the daytime oxidant that's really important. What is the mechanism that generates all this OH that generates the OH for the oxidation? It's actually involving this ozone that we mentioned earlier, okay, O3. So ozone will photolyze and produce an oxygen atom. And that oxygen atom is a very unreactive one. It's called O-singlet-D. And this will quickly collide with other air molecules and convert to a more stable state of an oxygen atom. But some of that O1D, O-singlet-D, will actually react with water and form our OH. Through this minor route is where we get our OH production. And it's dependent on the photolysis of ozone. In the boundary layer where we live, we have plenty of water typically, unless we're in a desert. So this reaction here, subreaction, is really important to generate these oxidant levels. Revisiting this slide here from before, now I've updated it a little bit. Now I'm showing the title is photochemical oxidation, right? Because we know that OH is based on photochemistry, okay? Photochemical production of it as an oxidant, so it can take care of its oxidation chemistry. So this is really what we're going to focus on in terms of this self-cleansing mechanism, in terms of its ability to scrub the pollutants from the atmosphere. Okay, and in doing so, we can understand that the OH photochemistry, because it is the primary oxidant in many cases, it's actually regulating the lifetime of these pollutants in many cases, right? So as these emissions are put into putting pollutants into the atmosphere, their survival is dependent on how quickly OH is able to remove them. So thinking about this idea of chemical lifetime, okay, we're going to represent it by the Greek letter tau. And so this is simply can be understood as equal to the inverse of the first order loss rates for that pollutant. Okay? So for instance, if our first order loss rates should have a unit of per time, in our case I'm going to use per second. And so we're going to revisit benzene again, this real nasty molecule. And for this one it's quite simple because it only reacts with OH. There are no other loss mechanisms that we really need to consider here in the troposphere. And this reaction with OH will generate an intermediary which is unstable and reacts with oxygen. And that reaction then will produce phenol and another compound called HO2, hydroperoxy radical. Okay? And then some other products at lower yield. This reaction will have what we call a bimolecular rate constant associated with it. So bimolecular, two-molecule reaction, right? And so you notice the units are cubic centimeter per molecule per second. In order to convert this rate constant to this first order loss, we need to multiply that by the oxidant concentration, okay? To eventually get to the lifetime. So we could, if we had measurements of OH, we could then apply those to this calculation. We don't necessarily have those for this example problem, wherever we're thinking about in type A. We could also derive the OH concentration. But for the purpose of this lecture, I'm just going to use a typical value that we might see. Okay, we usually think of a daytime OH concentration to peak somewhere in the million molecules per cubic centimeter range. So I'm using 1.2 times 10 to the 6 molecules per cubic centimeter. Taking the product of these two, the concentration and the rate constant, taking the product here in the denominator, and then taking the inverse will give us tau benzene, right? The lifetime of benzene, which will be calculated as 8 days. Now, for such a nasty molecule, you might think that this is still quite a long lifetime, right? Yes, it's true. Continuing to do its, have its health impacts and do its damage, it seems too long. So, of course, in this kind of case where our best line of defense is OH oxidation and it still has such a long lifetime, all we can really say is we should probably reduce emissions. Well, I'm not going to tell you to stop driving your car. Okay, we all need to get to work and school and everything. But smoking is also another source for benzene, okay? So I plead with you, stop smoking, or if you know anybody that's smoking, it could help us to reduce this problem. Okay, just my personal plea. Okay, we can extend this concept of lifetime to other chemicals. OH is reacting with all kinds of organics in the atmosphere and inorganics. And another one that's very interesting is formaldehyde, HCHO. It's not quite the nasty pollutant that benzene is, but it's really important to oxidation chemistry, and so I'm going to use it as an example here. And so when formaldehyde reacts with OH, it generates the formal radical, HCO. This is another radical species. It decomposes into carbon monoxide, a criteria pollutant, and in a hydrogen atom. And that hydrogen atom will then go on to produce HO2. That's the same molecule I mentioned in the oxidation of benzene, right? So if we take the product again of the OH concentration and the rate constant, we can then calculate a lifetime of benzene of 27 hours. However, that would only be based on the chemical lifetime of benzene and its dependency on this reaction with OH. So what I'm trying to, my point is that other compounds, some compounds, we need to consider a more comprehensive set of loss mechanisms, okay? Not just the reaction with OH that we calculated for benzene, but also other loss mechanisms. For instance, formaldehyde is subject to deposition. This is how quickly it deposits on surfaces. So we have a kind of an upper limit of the deposition velocity for formaldehyde at about 1.5 centimeters per second. If we assume a typical daytime boundary layer height of about 1 kilometer, we can calculate the first order loss rate due to deposition. Okay? Formaldehyde also photolyzes. Okay? So it also participates in photolysis reactions. And in doing so, it generates things like carbon monoxide and also that formal radical. So you can expect that photolysis of formaldehyde will then eventually lead to more HO2 as well, right? Okay. Now we have all these first order loss rates. We have the loss rate due to reaction with OH, which I'm terming K sub C. We have the first order loss rate due to photolysis, which is in the 10 to the negative 5 region, and the first order loss rate K sub D for deposition. Okay? We can sum these in series, okay, all these per second values or per time values, and then take the inverse to calculate the lifetime of formaldehyde, which comes out to just above 3 hours. So at midday, of course, this is a short, would be the tip of maybe a typical lifetime. But if we're calculating this for the morning, we're expecting much less light availability, lower photolysis, lower OH concentrations, because we know it's dependent on light. So probably a much longer lifetime, depending on the time of day that we calculate. Okay? So bear that in mind. Okay, so we have all this, now we have a good understanding of the pollutants, the oxidants, and the oxidation mechanism that occurs. With that, we calculated the chemical lifetimes, so showing how important it is for these oxidants to scrub the pollutants from the atmosphere. But actually, these oxidation mechanisms are involved with something else, another important concept, and that's ozone formation chemistry in the troposphere. Just a reminder, ozone, of course, up high in the stratosphere, it's a shield for us to protect us from UV radiation. But in the troposphere, it's a criteria pollutant, just like carbon monoxide, nitrogen dioxide. Okay, ozone is a health risk. And it's still a major problem in many areas of the world, including Taiwan. And it's also unique because it's not a primary emission. Okay, it's not something that we can just reduce emissions and get rid of ozone easily. It's a secondary pollutant. So it's really dependent on all this chemistry. As we can see here in this plot, these are some measurements from a research campaign. We can see that the OH concentrations precede, the peak of OH precedes ozone on this day. And this is fairly typical. So we can understand that the peak OH concentrations and the peak oxidation that's from OH is kind of fomenting the environment to produce a lot of ozone, okay, which will come afterwards. So this will lag behind a little bit all that photochemistry that's occurring. And just as a reminder about how harsh of an oxidant ozone really is, I'm showing some photos of our lung airways where they split into our two lobes. This is healthy airways. You can see are kind of crystal clear, a lot of airspace to breathe in and out with. Whereas these are inflamed, you can see that they're very almost swollen shut, right? So it's really hard to breathe. And this is what can happen when we're exposed to higher levels of ozone as a pollutant. And particularly for people with asthma, this is a major risk. But actually, ozone also negatively impacts plants, okay? Plants on their leaves have a hole, a pore called stomata, and through that stomata, it exchanges photosynthetic gases, which are very important, obviously. It generates oxygen for us to breathe. But it also is a place for ozone to deposit. And as ozone deposits, it's a powerful oxidant and it oxidizes much of the intercellular tissue. This is also very unhealthy for plants. Okay? So, where does this secondary pollutant come from? I told you that we can link it with some of this, with the OH oxidation chemistry, right? Well, yes, that's true, but we should first state that there is a background level of ozone that is naturally there, okay, before we even start to link it with the OH oxidation. We know that theoretically ozone reaches a photostationary state with NOx, which is the combination of NO and NO2. Okay, and so what we have here is we have photolysis of NO2 generates NO, okay, and then eventually ozone. But then those two products react together, NO and ozone, and reform NO2. Okay, so we have this cyclical process that generates ozone but then destroys it in the next step. So kind of a net zero impact on ozone overall during the daytime. However, we know ozone is involved with other mechanisms in the atmosphere at the same time. We already introduced one earlier. We know that ozone is photolyzing and produces OH through this minor route here. Okay? So, how does that impact? Well, we know OH is produced, and we know OH is continuing to oxidize all the pollutants. So, as an example, OH is also oxidizing carbon monoxide, something we've mentioned several times already. As a pollutant, we mentioned it. And when it oxidizes carbon monoxide, it leads to production again of this HO2 that I've mentioned. Crucially, this is the link, is that HO2 then reacts with NO, okay, and converts NO to NO2. Now, in the photostationary state, we only had ozone reacting with NO to produce NO2, right? So we would be destroying ozone in the process of reaction with NO in that conversion. But now we have HO2 reacting with NO, producing NO2, which is our precursor for ozone, and at the same time, we're not destroying ozone to get there, like in the photostationary state. Finally, the last important bit on this slide is that HO2 also recycles back to OH. So there's still plenty of OH to continue oxidizing the pollutants, okay? And so you can imagine this cycle could continue several times and keep on converting NO to NO2 and keep producing more and more ozone on top of the background levels of ozone that are there. But that's not all. We already know from earlier slides that there are other oxidation mechanisms that also generate HO2, right? So not just oxidation of carbon monoxide, but also oxidation of benzene, oxidation of formaldehyde, and these are just two examples. There's actually many chemicals that have similar end products. And so we can understand that there's several ways to actually propagate from OH to HO2, and this HO2 is of course the element that is the molecule that's converting the NO to NO2 in excess over the photostationary state with no ozone destruction as a result. Okay, so these are really some examples, some basic understanding of how this tropospheric ozone chemistry occurs. Okay, actually, there's additional mechanisms that are going on at the same time, and it becomes more and more complex. And I'd love to continue this discussion, okay, but for the purpose of this lecture, we'll kind of wrap up the story here. But I hope that I've convinced you how important the OH oxidation mechanisms are to ozone formation, actually, okay, in the troposphere. And maybe at some point we can explore the further mechanisms together. Okay, so thank you for everybody for attending, and I'd be happy to take any questions. That was about 20 minutes. Okay. Students? Hi.
I guess that OH radical is a really short lifetime. So how did you assume that there is a constant concentration of OH radical in the atmosphere?
Yeah, it's true. So the lifetime basically is a second or less. Yeah, a second would even be quite long. So we can understand in the daytime, basically if we know the basic production mechanisms, like the ozone photolysis, and we know the loss mechanisms. So one of them we didn't introduce here, OH reacts with NO2. Okay, and this is a big loss mechanism. It removes OH from the system. So if we take all the reactions that we know, we can set up a basic steady state mass balance equation and do a calculation for its concentration, basically. This is one of our derivations. And so, yes, you're right, there is variability in the OH concentration for sure. But we could do that calculation with basic background levels of ozone, tens of ppb, basic background levels of NO2, and we'll oftentimes get at some level around 1 million molecules per cubic centimeter. One thing I didn't really emphasize is that I really wanted to focus on urban chemistry here a bit, although I didn't introduce a bunch of different chemicals. I thought urban chemistry would be more applicable, for all of us that live in Taipei. But the chemistry actually changes a lot if you go to more remote areas. Okay, so just as a taste, that I emphasize the HO2 plus NO is the mechanism that recycles everything and produces a lot of ozone. Actually, if you go to a remote area where the NO is very low, then your whole ozone production mechanism, a lot of it changes, and you're much closer to background levels. Hi.
Very nice lecture. Yeah.
Thank you.
Thank you. And I'm just wondering, is there any competing mechanism that destroying ozone instead of amplifying, like the NOx?
Yes, for sure. And this fits into what I was saying earlier, a little bit to what I said earlier, in that we didn't show the full complexity here. But basically, one of them, for instance, is, for instance, the photostationary state is always occurring, right? You still have NO reacting with ozone. It doesn't go away. And that reaction is very fast. Okay. So you can think of the additional ozone or additional NO2 that's produced is sort of on top of that a little bit, right? But it's enough, and it's enough to generate excess ozone above the background level. Okay. But there are other mechanisms as well. For instance, HO2 will react with ozone. And this is a major reaction in lower NOx conditions. Okay, so if you go to more remote areas, HO2 plus ozone is actually an important reaction. But if you're in an urban, down at street level, it won't be as crucial. Ozone itself is also, like, as you know, an oxidant. So it reacts with a lot of organics as well. I gave an example of benzene, but its reaction is very slow with benzene. But it does react quickly with a lot of unsaturated compounds, meaning compounds with double bonds. Okay, so propene, butene, all these, which are common emissions from anthropogenic sources. And so ozone is really has its own importance to these oxidation mechanisms as well. I have a question for you. I'm just I'm lecturing in English, and I want to speak slow enough that I don't want to confuse anybody. Also, I'm using some chemistry terms, and I know we're all in atmospheric science here, so I just want to know, did I speak too quickly? Would you like me to slow down a little bit in my lecturing speed, or what? I can take your answer offline, it's fine. But anyways, I would love your feedback if you have an opportunity.
For me,
Yeah.
the variance of English ability in English and in atmospheric science department or other departments, there's a big variance of English ability. So for me, I think it's just okay. It's a little bit fast, but the comprehension is just enough for me.
Okay.
There's enough reaction time.
Okay. Great. Reaction time. Good. like a fun. That's so funny. Well, and you're a graduate student, right?
Yeah, I'm studying for master's degree.
Okay. So you've been in more lectures than an undergraduate student, probably more English lectures as well.
Maybe.
Yeah. So how about Beck? You're an undergraduate student.
Yes.
Can you give me some feedback? I don't want to put you on the spot, but
I think the English is also a little fast
Too fast.
that I can easily understand. The word you use in the lecture is, I think, it's really easy to understand. So that would be a great way to talk. I want to say that both I have a little long time didn't review the name of the chemical.
oh yes,
Of
the chemicals, the molecules.
yes.
Yeah.
So when I suddenly hear the vocabulary, I will feel a little.
Yes.
Feel I don't know. How
You need to remind yourself, perhaps. Yeah.
Yeah, so I think for a new or a young student, they may need some background information, or maybe it needs the how do you say the just like CO2 will be more easier for students to understand than
Oh, I see.
like,
Okay.
just like maybe try to use some this kind of word on the hormone will help students to understand.
Okay. Yeah. Good point. Thank you. Okay. Yeah. Hi.
I want to feedback a little bit on chemical terms like you use the pseudo first order reaction to explain the concept of lifetime, but I think that in atmospheric science background can't get this concept easily.
Oh. Okay.
Because I think that is some terms in chemical kinetics, and for them will not get it easily.
Okay. I should spend a little more time explaining this concept. Perhaps one extra mathematical slide. Yeah, thank you. Okay, well thank you for all the feedback. Thank you again, Professor Hong, for hosting. Thank you for Ding Wu showing up and being a great audience. So thank you all.
Okay, great. Let's thank Dr. Griffith again.因为说不定挺大会看，比较容易比较可以接受。
我要上去问问题。维姐，问问题。
像是3:30。
对，我们好像还要等半个小时后，给他休息一下。慧敏第五。你好，你